Good morning, all the participants. First of all, I'd like to thank the organizers for having given me this opportunity to share some of my works. And also, I'd like to thank once again for permitting me to participate in this through this online platform. I'll be talking about discontinuity induced mixed mode oscillations in a Memristive nodal Lakshmanan Chua circuit. This work was carried out under the guidance and collaboration of my professor M. Lakshmanan, who is in the Center for Nonlinear Dynamics, Bharatdasan University. I am presently working at Jamal Ahmed College as an associate professor. Now, I'd like to present the overview of my talk. First, I'll be introducing the concept of mixed mode oscillations, then the concept of memristors, then memristive Murali Lakshmanan Chua circuit, then memristive Murali Lakshmanan Chua circuit as a non-smooth system, and then discontinuous bifurcations that are admitted by this Murali Lakshmanan Chua circuit with memristor, and then mixed mode oscillations, and finally closing remarks. Well, mixed mode oscillations correspond to a kind of dynamic behavior wherein the system may alternate between two different types of oscillations. One is a large amplitude oscillation with a very short time scale, and another one, small amplitude oscillations with longer time scales. They have been found to arise in many systems, chemical, physical, as well as biological. I'd not like to elaborate on this because literature is strewn with so many examples of mixed mode oscillation shown by many diverse systems. Now, let me go to the concept of memristor. In the year 2008, the presence of memristor was first reported by HP Labs in nanoscale devices, solid-state nanoscale devices. Earlier in 1971, it was predicted by circuit theoretician Leonard Chua purely on empirical basis. So a memristor is a two-terminal device which exhibits a pinched hysteresis loop in the VI plane when driven by some bipolar voltages for any initial conditions, and the mathematical constitution the relation is given as f of q comma phi is equal to 0. This memristor may be of two types. One, it may be a flux control device or it may be a charge control device. For a flux controlled device, the constituent relation is given as I is equal to W of I V of t, where W of I is the rate of change of charge as a function of flux, dq by d phi. And this ratio we call as memdectance because it has the dimension of conductance. The other one is the Q control memristor, which has its constituent relation as V of t is equal to mq of into I of t, where mq is equal to dq by dq, d phi by dq. That is rate of change of flux as a function of charge across the memristor. This has the dimension of resistance, and therefore we call this as resistance. Therefore, we call this quantity ratio as memristance. In the year 2008, Ito and Chua proposed theoretically a model for memristor which has piecewise linear characteristics, and they proposed both the cases for flux control as well as charge control. Now, I am using the idea for flux control memristor proposed by these people, and the expression for charge through the memristor is given by this equation 4. It is similar to the equation for a Chua's diode in the VI plane. The difference here is it is in Q5 plane. The characteristic of this memristor, theoretical characteristic, is plotted here on the phi Q of phi plane, and the slopes are the memdectance of the device. Now, the same memdectance as a function of flux shows a variation here. So at certain instant, when the flux changes from -1 to higher values, lower values, it is W1. From -1 to +1, it is W2, and above +1, it is W3. So that variation, corresponding variation on the phi W of phi plane is seen here. The memristor has many circuit theoretic properties like memory nature, resistive switching, pinched hysteresis loop, and modulating ability. The memory nature is explicit from the expression for phi, which follows from Faraday's law. So if you were to want to calculate phi, it is integral of V of t d tau, where V is the voltage across the device from some time to the particular instant at which you want to calculate, and this could be rearranged like this. Conveniently, we can have phi of t naught is equal to 0, and we'll be having phi of t as integral of V of t tau d tau. So the flux across the device is an integral of the voltage across it for a certain interval of time. This shows the device has a memory nature. The memristor also shows resistive switching and pinched hysteresis curve. When memristor is energized by a sinusoidal forcing, the memdectance as a function of time is given by W of t is equal to WA plus WB V of t, where WA and WB are some values, certain values, discrete values, and V of t being a sinusoidal voltage can be represented by this form. V of t is a square wave voltage. It can be represented by this form. And based on this, we can have two different values of memdectance as functions of time. It is W1 equal to WA at low off stage, and W2 is equal to WA plus WB into this simplified value 4 into Vm by N into pi for integral values of N at constant frequency Fm. So this causes the resistive switching in the TW plane and hysteresis in the VIT planes. So these are shown here. Theoretical simulation of these characteristics are shown here. We find the memristive switching here and also the memristive switching in the V of t, I of t plane, giving rise to pinched hysteresis characteristic. This is considered to be a fingerprint for memristor. Further, due to a resistance switching, we can have the memristor to possess modulating ability. When a pure DC current is passing through the device, the variation in memdectance in current is shown like this. But when additional sinusoidal forcing is given to it, this memristor introduces additional frequencies. The mathematical equations are shown here, and the current with additional frequencies being introduced, that is after it is modulated, is shown in this diagram. And as a proof of it, from this expression we find there are three different frequencies: the external frequency, the additional frequency Fe plus 2n minus 1 Fm, that is Fm stands for modulated memristor frequency, Fe for external frequency, and here with the minus term here. So two additional frequencies in addition to the external periodic frequency are present. And that is shown clearly in the power spectrum graphs. Based on this theoretical idea, we try to construct an analog model, experimental model for the piecewise linear memristor. So it is a very simple circuit which we proposed, myself, Srinivasan, Murli, and my professor Lakshmanan proposed in the year 2011. It has a very compact design. It has an integrator module, and then this integrator module is used for integrating the flux to give the voltage. Then this window comparator module, switching module, and then negative impedance comparator converter. The analog switch which we used is AD7510D, DJ, and for all these we had used the operational amplifier TL0081. The simulated and experimental VI characteristics are shown here, and the resemblance is remarkable. Next, we move on to the system that is under consideration, the Memristive Murli Lakshmanan Chua circuit. The classical MLC circuit was introduced way back in 1994 by Murli and Professor Lakshmanan using Chua's diode. It is a simple two-dimensional circuit, series resonance circuit, and it is known to possess rich dynamics. It has been studied by many persons. Experimental realization and experiments have been performed on that. Control and synchronization studies have been made. Spatio-temporal dynamics, intermittency studies, beats, and even inductorless realization of MLC circuits have been carried out. So it still continues to evoke response in the nonlinear electronic community. Therefore, we try to modify this circuit by introducing the memristor, replacing the Chua's diode. The circuit equations are shown here, which are obtained by using Kirchhoff's laws, and using these rescaling parameters, the normalized equations are shown here. Now, once we have this MMLC circuit, Memristive Murli Lakshmanan Chua circuit, we will consider it as from a different perspective, that is from non-smooth bifurcation theory. We will consider this as a non-smooth system because it has a discontinuous nature because of its non-linearity, namely the memristor. The memristor will switch state either from a higher on state or to less conductive off state at plus or minus 1 values of the various system variable x. Consequently, the entire phase space for the system D can be divided into three subspaces, S1, S2, and S3, with the central region being S2 and outer two regions being S1 and S3. The two switching manifolds, sigma 1, 2 and sigma 2, 3 are symmetric about the origin. These are also the discontinuity boundaries about which bifurcations will take place and which we are going to talk about. These are defined by zero sets of smooth function H1 and H2. Obviously, if we assume x is equal to -1, we'll be getting 0, and x is equal to +1, again we'll be getting 0. Therefore, the zero values of H1 and H2 scalar functions will be defining the discontinuity boundaries. The equations, circuit equations can be reformulated in non-smooth form like this, where x dot is equal to F2 and F1, 3. These are smooth vector fields, where the vector fields are defined by equation 17. Obviously, since the vector fields are symmetric about the origin, we have A1 is equal to A3. The curve, the slope of the characteristic curve of the memristor in the outer regions, 1 and 3 regions, and A2 is the slope of the curve in the inner region. Now, this memristive MLC circuit is a flip-of flow because the vector fields F2 is not equal to F1 at any point on the discontinuity boundary. Similarly, the vector flow F2 is not equal to F3 on any point on the discontinuity boundary sigma 2, 3. That means the system has a degree of smoothness R is equal to 1, and therefore we consider this in the for this case as a flip-of flow. Then we have found out the equilibria of the circuit. We have found out the equilibria points of the circuit we have identified three sets. One is trivial equilibrium point, another two admissible equilibrium points, which are symmetric above the origin, and two boundary equilibrium points. These equilibria satisfy the general conditions for non-smooth systems as applicable to our system. We find here the equilibrium points E plus and E minus, which are symmetrical about the origin, being traced here. Earlier works on this circuit, we have led to identification of many discontinuity-induced bifurcations, like grazing bifurcations. We have studied grazing bifurcations leading to chaos, transient hyperchaos, and hyperchaotic beats in this circuit earlier. We had studied Hopf bifurcation, Neymark-Sacker bifurcations, and then sliding bifurcations. We have identified three different types of sliding bifurcations: grazing sliding, crossing sliding, and switching sliding. Then we have also studied control of chaos using state feedback technique and synchronization of chaos using observer-based adaptive techniques. Now, we wanted to find out what other types of the dynamic behaviors the circuit admits, and therefore we found out in our observations the circuit admits slow-fast oscillations. These slow-fast oscillations are mixed mode oscillations. We believe arise due to discontinuity-induced Hopf bifurcation and adding sliding bifurcations. To study these, we fix the parameters of the circuit as this one. And in addition, if we use an additional quasi-periodic force, we find that these mixed mode oscillations also show beats phenomena.
Hi, sorry to interrupt, Ahmed. We just have 2 minutes left before the break.
Okay, ma'am.
Yeah. Thanks.
So for this, thank you, ma'am. I'll complete it. Discontinuous Hopf bifurcations were identified using Clark's Jacobian theory. And we had shown the graph here using Clark's Jacobian theory. Then we have seen observed sliding bifurcations. The conditions for adding sliding bifurcation, the definitive conditions, non-degeneracy conditions, extra degeneracy conditions for a general system have been given, and then for our MMLC circuit have been given. And then the zero discontinuity mapping corrections were carried out for our circuit, incorporated in our numerical simulations. So we find here for different values of parameters, we find slow and fast oscillations. We find in this region large amplitude oscillations with a short time scale and small amplitude oscillations with large time scales. For another set of parameters, when quasi-periodic forcing is added, we get beats in the system, showing simultaneous occurrence of both mixed mode oscillations and beats. The time series is shown here, and a small segment of this time series is blown up for clarity. So this is another excellent show of beats mixed mode oscillations in the system for another set of parameters, and this is the time series plot of the same. So to close or conclude, we have seen the existence of memristors, their circuit theory properties such as memory nature, resistive switching, pinch hysteresis, and modulating ability, the design of an analog piecewise linear memristor and its characteristics, the realization of memristive MLC circuit and its circuit and normalize the equation using proper rescaling parameters, the MMLC circuit in the framework of non-smooth bifurcation theory, the mixed mode oscillations in the MMLC circuit, and reason they are arising as due to discontinuous Hopf bifurcation and adding sliding bifurcations. Also, we have shown the numerical results of simulation of MMOs. Thank you for your patient hearing.